Hi there and welcome to my presentation on ECS systems and optimization. Today we're going to be talking about what is ECS, what makes ECS so optimal, when to and not to use ECS, and then finally ECS in C++. So starting off, what is ECS? So the basic concept of ECS is a way of organizing data in a world that you want to populate with things. These things may have mechanics that are similar to each other while allowing them to still be unique. Looking at this from an object-oriented approach, we have the base class thing, where all other things inherit from. Any given class can only inherit directly from a single parent. A car and a truck have wheels because they inherit from a land vehicle, and a boat and a jet ski have hulls to float on water because they inherit from a water vehicle. But what about a hovercraft? This can move on both land and water. Now there are ways around this via the use of interfaces, however a better solution would be to build with the limitations in mind. This is when the entity component system comes into use. With ECS you start to use a base thing. However, as opposed to inheritance, instead of having a class inherit from the base entity, you instead add components to the entity. A component is strictly for only holding data and no functionality is coded into them. An entity can hold many components, each providing different functionality to the entity, such as rendering, shooting, or moving. That functionality is instead moved into one or more systems which operate on each relevant component. This allows for each component to not be directly linked to its functionality, allowing the data to be unique, while the method that uses the data to remain the same. Looking at the move component here, we can see it holds only 3 pieces of data. This is all the data we need to pass across to the move system. When it's time for the system to run, it will iterate over every component that type in a scene, taking in data for each component and using it to carry out its function. However, you may be thinking, Unity already uses ECS, but you'd only be half right. Standard Unity uses a mixed version of the ECS concept. Each component inherits basic functionality from the monoBehavior class, then you're able to add your own data to the component. Beneath this, Unity has merged the system directly into the component, allowing you to create the functionality that uses the data to be carried out within the component itself. While this seems a better way for ECS to work, it has a massive impact on performance. By mixing the components with the system functionality, it places the class instance of each component in a scattered effect throughout the heap memory. This means that for each component on a game object or entity, we'll have to traverse the memory to find each component. True ECS, as described earlier, allows many entities to have the same component, each with unique data. However, the functionality that uses this data is abstracted out. So this is where we look at what makes ECS so optimal. With ECS, by moving the system out of the component, this allows for each of the same component to be stored in a contiguous list in memory. This ensures that the system only has to iterate through that list without having to traverse memory. This makes for the memory allocations to be much more compact as opposed to the scattered effect that Unity uses. If we take a look at this transform component that Unity uses, we can see that it also includes lots of functionality that a particular component might not need. Using the move object component as an example, all we need is a vector3 position, a vector3 direction, and a float speed. When this is passed into the system, it will move our entity forward, and as a result, if we were to do the same with Unity's transform component, we would have no need for the rotation method or world to local matrix methods, just to name a few. By only including what we need, we further reduce memory usage by not including functionality that won't be used. This is what enables ECS to far outperform the standard Unity system. If we take a look at the graph to the left, we can see that while performance of the CPU has dramatically increased over time, the performance of memory hasn't done so at the same rate. By utilising this data, we can focus on removing all the actions that take the most time when working with memory, such as traversal and allocation. By abstracting each component into a contiguous list, this allows the CPU to save time finding and allocating new memory or traversing to find a component. Using systems to carry out functionality also allows the CPU to parallelize each system, as they are only carrying out a single task to an array of components. Another benefit of using a contiguous list to store each component is that the CPU is more likely to have each component stored in its cache, as when deciding on what to cache, the CPU stores memory locations close to the most recently accessed one. When to and not to use ECS. As we have learned, ECS is highly efficient at utilising the strength of the CPU with memory allocation and traversal. It is highly efficient and the system can iterate over all components at a time rapidly thanks to contiguous storage. As a direct result of using systems, we also have lower memory usage due to only including the data and functionality we need and not having to repeat functionality, which could be the case in some inheritance situations. We also have compact memory allocation, allowing lower level access to each component should the programmer need to. However, ECS does have some downsides. While providing lots of benefits, utilising ECS can be rather difficult because of the complexity it involves. Moving a development team from the Unity-based entity component system to an entity component system could take some time, as the mentality behind creating game functionality is quite different and can prove more of a hindrance, especially if developers aren't as experienced with programming. Another key takeaway is that systems are dependent on ordering. What that means is that before implementing a component and a system, you need to think about what data it needs to function. If it relies on a transform component, but the transform system runs all the components after your new component, the data fed to your component is always going to be old or outdated. This requires lots of design preparation before a new entity and system is implemented to avoid unexpected results. When should you use ECS? Now, ECS is a perfect use case for large-scale simulations where there are a huge number of entities in a scene, each with their own functionality. This is especially prevalent when on low-end devices or mobiles, as processing power is limited and every optimization matters. Here is an example of how I've used this concept of ECS in my game engine, created with C++. I decided that I want to take a similar approach to Unity by integrating all the systems into the component itself. However, instead of scattering each component throughout memory, I've decided to create a fixed contiguous vector which stores each component. Although each component functionality will be stored multiple times, I've utilised the contiguous vector to ensure that the CPU does not need to traverse through the memory to find each component type. When creating components, I utilise a bit set, which with a predefined length allows me to set a bit at the position which directly correlates to an ID of a component, to either true or false. For example, if I have a component whose ID is 3, the third number in the bit set will be set to true. By doing this, I can then determine exactly what components each entity has by passing the bit set into a method which will then read it and find all the components allocated with a specific entity. This works extremely efficiently, and I highly recommend this method to anyone looking to experiment with ECS on their own. Thank you very much for listening to my presentation on ECS, and I hope you learned something new. Enjoy the rest of your day.